Dear students, welcome to this lecture on digital logic and system design. In the last couple of lectures in this series for this course, we have seen the design of sequential circuits based on different flip-flops. We saw one design using RS flip-flop, another design using JK flip-flop, then T flip-flop. So all the different flip-flops we have seen that had been used in the design of sequential circuits. Uh, Today we are going to see a counter that will be a synchronous counter. In fact, we saw a synchronous counter on the previous turn also, but that was a regular 3-bit counter, a modulo 8 counter that counts from 0 to 7 and then resets to 0. Today we are going to see a counter which may have an arbitrary count sequence and may not necessarily have all the possible counts. For example, the counter that we have chosen, the state diagram can be depicted like this. So my counts are in the sequence 0, 1, 2, and then 4. 3 is skipped, and then 5, and then 6, and 7 is skipped again, and then I am getting back to 0. So this is the count sequence. Suppose I want to design a counter with this count sequence. In fact, this sequence may not be in order even. I may be going for 0, 4, 2, 7, 6, like that. Any arbitrary count sequence can be taken into account to design a counter accordingly. But in such cases where the count sequence doesn't encompass all the possible counts, in that cases, in all such cases, we should have a self-starting counter. A self-starting counter is the one that can start from any state but eventually reaches the normal count sequence. For example, when we switch on the power of such a counter which doesn't have count 3 and count 7 in it, and by chance it starts with the count 3, so I should have the provision that in on the occurrence of the next clock pulse, this should lead to one of the counts in the count sequence, so that the clock pulse next to it, it gets into the main stream of the count sequence. Likewise, if we have the power on and the counter state is 111, then in the next clock pulse it should lead to one of the count sequences. I've just arbitrarily chosen this 011 to be going to 100. It may go to any one of them. It may go to 101 or to 110 and 0, or 001 or 000 even. Likewise, 111 may go to any of these count sequence, right? But it makes more sense that we put the count in the higher possible count. Like for example, 3 should lead us to 4, 7 should lead us to 0, so that next time when it comes, it should go to 101 and 110 and so on, right? So self-starting counters are those counters that may start from any state, but eventually it gets into the normal count sequence that we have designed the counter for, right? So suppose this is the state diagram of the counter that we want to design. Now we will follow the usual steps. Present count state is 000. What should be the next count state or sequence? It should be 001. With 001 being the current count, the next one that I want to see is 010. Over here you see I am presenting it in two different columns. In the previous lecture, since the count was very regular, 0 1 2 3 4 5 6 7 and 0 1 2 3 5 0 1 2 3 4 5 6 7 and back to 0 and so on. So we need not give this column in that case, because we knew that it is going from this to this to this to this. So we directly found out the required flip-flop inputs by giving just one column as the count sequence column. But over here the count sequence count sequence is not that regular. So that is why, in order to make things explicit, I am putting it in two different columns. So present count state, if it is 000, the next count state should be 001. If the present state is 001, then the next state should be 010. That is what I state here. If the present state is 0 1 0, then the next state should be 1 0 0 0. That is what our state diagram of the counter shows. So we do not have 0 1 0 leading to 0 1 1, right? That is why we have to give it into different columns. Again, 0 1 1, although it is not a part of the count sequence, but in order to make it a self-starting counter, I should get the 0 1 1 leading to one of the possible states. It is more logical to make it go to 1 0 0, because this is 0 0 1 3, so it should lead to 4 in the next count sequence, but that is not necessary. That is what I want to emphasize. It could go to any of the possible states. So 0 1 1, if it is the current count, then the next count state should be 1 0 0, right? And then 1 0 0 should lead to 1 0 1, and 1 0 1 should lead to 1 1 0. So 1 0 1 leads to 1 1 0, and then 1 1 0 should lead to 0 0 0 and not 1 1 1. So again, that irregularity in this particular counter design. 1 1 0 is 0 0 0. Again, 1 1 1 is one of the count sequences, is one of the count state that is not a part of the count sequence. So I should make it lead to one of the possible count states or the valid count states. So what I can choose more logically is to get this lead to 0 0 0, right? So 1 1 1 0 0 0. So I can say that 1 1 1 corresponding to 1 1 1, this next count state is basically anything but 0 1 1, right? Why? Because 0 1 1 is again not in the count sequence. So corresponding to 1 1 1, the next state could be anything but 0 1 1. Likewise, for 0 1 1, it could be anything but in fact, it could be anything but 0 1 1 itself and 1 1 1 also, because and the same holds true for 1 1 1 as well. It could be, the next state could be anything but 3 and 7, but 0 1 1 and 1 1 1. If suppose the next state I choose it to be 0 1 1, so it will be caught in an infinite loop. It will keep going at every clock pulse. It will keep counting 3 3 3 3 3 only. Likewise, if there is a self loop here, then it will go on counting 1 1 1 again and again and again, right? So I have, chosen the present count state and the next count state for these states according to the state diagram, and for these two leading us to 1 0 0 and 0 0 0 respectively, in order to make it a self-starting count. Now, having explained this, the next part is required flip-flop inputs. Once again, I must be using the excitation table, which you should have memorized. Okay, in case you haven't, I'm reproducing it here. This is the excitation table for the JK flip flop. So after getting these two columns, I should make a choice as to what kind of flip flop I want to deploy or I want to have in order to design such a counter. So suppose I say that I want to do it using JK flip flop, then I should have three flip flops, one flip flop representing one state, right? So correspondingly, the two inputs will be named as JA-KA, JB-KB, JC-KC. So these are the J and K inputs for the flip flop which represents state A. JB-KB are the J and K inputs respectively for the flip flop that represents state B, and JC-KC are the inputs to the flip flop that represents state C. So now let us see A to A to A. 0 to 0. I know 0 to 0 is 0 cross. Again, 0 to 0 is 0 cross, taking from the excitation table. Then 0 to 1 is 1 cross. Right? Excitation table tells me that. Again, 0 to 1 is 1 cross. Then 1 to 1 is cross 0. 1 to 1 is cross 0. 1 to 0 is cross 1. And 1 to 0 is cross 1 again. So I get JA and KA inputs required for affecting this state change for state A. Now coming to state B, 0 to 0, JB KB should be 0 cross. B 0 to 1, it should be 1 cross. 1 to 1, it should be cross 1. 1 to 1 is it should be 1 to, okay, let us start again. 0 to 0 is 0 cross, 0 to 1 is 1 cross, and then 1 to 0, 1 to 0 is cross 1, 1 to 0 is cross 1, then 1 to 0 is cross 1 again, and then 0 to 0 is 0 cross, 0 to 1 is 1 cross, then 1 to 0 is cross 1, and 1 to 0 is cross 1 again. See, 1 to 0 is cross 1, right? So we get the required flip-flop inputs for the flip-flop representing state B. Again, for represent the flip-flop which is representing C, what are the flip-flop inputs required? 0 to 1 is 1 cross, 0 to 1 is 1 cross, right? Then 1 to 0 is cross 1, 1 to 0 is cross 1. Then 0 to 0 is 0 cross, 1 to 0 is cross 1, 0 to 1 is 1 cross, and 1 to 0 is cross 1, 0 to 0 is 0 cross, and 1 to 0 is cross 1, 1 to 0 is cross 1. So with the help of the excitation table that you should have memorized, I can find out the required flip-flop inputs for the count sequence that is represented in this state diagram. Now what is next? I should get the equations of these flip-flop inputs in terms of the states A, B and C. So JA as a function of ABC, KA as a function of ABC, and so forth. Again, as we have explained earlier in the previous lectures, there is no explicit input and there is no explicit output. The states themselves are the input and the output for a counter, right? The present state tells you the present count, and the next state tells you the next count that should be on the occurrence of a clock pulse, right? So there are no explicit inputs and outputs over here. So next we have to draw the K maps. So for JA, A, B, C are the states. So let us see 0, 0, 1, 1. So 0, 0, 1, 0, 0, 1, 1. And then cross, 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 4 crosses. So cross, 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 cross. I can combine these two. I can get JA. A will be eliminated. And I will get C also eliminated, and I'll get B. So JA is equal to B is my first design equation. Likewise, I should populate the K map corresponding to the input terminal KA. And what is that? Cross, 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 4 crosses, cross, 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 and then 0, 0, 1, 1. So 0, 0 we don't represent, so 0, 0, 1, 1. Again, this larger square may be formed, and over here A gets eliminated again, and C also gets eliminated. What do I get is just B. So KA is equal to B is my second design equation. Now coming to JB, let us see. Coming to JB, how can I populate it? JB is 0, 1 cross cross. So 0, 1 cross cross, right? And then 0, 1 cross cross again. So 0, 1 cross cross. So one learning lesson from this, whenever we are combining them, I need to combine this only. There is no need to combine these 4 because they are don't care conditions. If I combine them also, I'll get plus something, right? So that will be extra because they are don't care conditions. I need not necessarily cover all the don't care conditions. I should cover all the ones nevertheless, right? So if I consider this square, all the ones will be covered, and these two don't care conditions will help me in minimizing it further. So when I do it, A gets eliminated, I get C only. So JB is C. B gets eliminated, A gets eliminated, I get C only. Again, designing for KB. Let us see. Cross cross 1 1 and cross cross 1 1, right? So cross cross 1 1, cross cross 1 1. I can form the biggest possible, rectangle here, which encompasses all the 8 entries for this K map. So I can say that KB is equal to 1. If I treat them as 1 1 1, so the entire thing will be covered. So I should get KB is equal to 1 because all A, B, C, everything will be eliminated. So KB will be 1, right? Never get confused that all of them are being eliminated, so it should be 0. No, they're all treated as ones. Okay, so everywhere 1 means KB should be what KB is 1, right? Now coming to JC again. JC, let us see how can we populate it. 1 cross 0 cross. So 1 cross 0 cross and then 1 cross 0 cross. So 1 cross 0 cross, right? Again, I can combine these four. Do not combine these four because they don't care conditions, right? I need to cover only all the ones. I need not necessarily cover all the don't care conditions. I'll just consider these two don't care conditions. So effectively what I'm doing, I'm treating these two don't care conditions as 1 1 and these two don't care conditions as 0 0 because this is suiting me. This is helping me in obtaining the best minimization, right? So A gets eliminated, C gets eliminated, B dash remains. So JC is equal to B dash, right? Again, KC is cross 1, cross 1, cross 1, cross 1. So cross 1, cross 1, cross 1, cross 1. Over here, I'm treating all the don't care conditions as 1 because it is helping me in forming the biggest possible rectangle, and KC will be 1. So these are my design equations. I can now draw the circuit for the counter that we have designed, the self-starting counter for which we have given the state diagram over here. So I'll take these six equations and I'll put them here. JA is equal to B, KA is equal to B as well, JB is equal to C, so JB is equal to C, KB is equal to 1, so KB is equal to 1, and JC is equal to B dash, so JC is equal to B dash, and KC is equal to 1, so KC is equal to 1. I'll put 3 JK flip-flops, each flip-flop representing a state each. Suppose this is the flip-flop which represents the state A, this is the one which represents state B, and this is the one which represents state C. Correspondingly, this will be KA, JA, KB, JB, KC, JC. Now, KA, what is KA? KA, it says is B. So, where will B come from? The past state, right? So, this B will be fed to A. And so is JA. So, what I'm doing, I'm taking B from here and feeding it to both J and K. So, these two design equations are taken care of. Now, coming to this design equation, JB is equal to C, right? Where will C come from? The previous state, right? That will be fed to C. And KB is equal to 1. So, KB is permanently connected to 1. Again, JC will be this terminal. This is JC is B dash. And where will B dash come from? If this is B, the past state, then Q dash corresponding to this Q will be B dash. So I'll just take this B dash and feed it here. So JC will become B dash. We should not be putting an inverter here and giving it to J because that inverter is extra. Your design will become inefficient. Why put an inverter when you are getting Q dash here itself, right? That is one of the reasons why the flip flop. I'm just trying to make you recall that the flip flop inputs corresponding to RS flip flop SR being 1 1 is indeterminate because in that case our condition of having these two as complement of each other, that condition gets hampered, right? So we have in fact done it in such a way that they should be complement of each other. So why not use it? Why inverting it and giving it to JC? Just use this inverted version which is already available. So JC will be B dash and KC is again permanently connected to 1. So this will be your counter which counts in the sequence 0, 1, 2, 4, 5, 6, 0, right? 3 and 7, they are being directed to 3 is being directed to 4 and 7 is being directed to 0 in order to make it a self-starting counter. This will be the logic diagram for the self-starting counter, right? So this is about the counters. Again, the clock pulses are tied up together, and these are the count pulses that are given to all of them at the same time. So that is why this is a synchronous self-starting count, right? Synchronous self, because all the flip flops are synchronized by the same count pulses, right? So this is synchronous self-starting counter with the count sequence that we have specified earlier, right? Now next we are going to study the registers, right? Just as our the flip flops, they are the basic building block of a sequential circuit because they can store one bit of information. That bit of information could be either 0 or 1, okay, whatever, they store it, right? uh, we should try to make it a word storage now. There are several bits that I want to store as a binary word. That may be a byte or any generic binary word of n bits, right? So I should grow that single storage into the x direction in order to get a what is called a register. So a register is basically the storage of n bit information. That is the storage of n bit information. So next we are going to study the registers. Let us see. A register is a group of binary storage cells suitable for holding binary information. A group of flip-flops constitutes a register. Since each flip-flop is a binary cell capable of storing one bit of information, an n-bit register has a group of n such flip-flops. An n-bit register will have a group of n such flip-flops, right? So this is what a register is, right? It is a group of binary storage cells for storing several bits as a binary word, right? N bit register means it is capable of storing n bit of information, and correspondingly it will mean that it has n bit flip flop, right? This is the simplest form of a register in which I'm employing 4 D type flip flops. Now you will realize the importance of the D flip flop. So this becomes a 4-bit register, the simplest form of a register. What will happen whenever the clock pulse becomes active, right? Since these are all positive as triggered, so active means whenever the clock pulse goes from 0 to 1. Whatever information you will put here, the same will get stored in this D flip flop, right? Apparently, earlier D flip flop seemed to be a device. Why is it there? 0 is being stored as 0, 1 is being stored as 0. So can't we have just a wire? No, a wire will not have storage, but a flip flop will have. What will happen when you make this clock pulse active, and suppose you apply 0011? I'm just giving an example. 0011. When the clock pulse gets active, this will store 0, this will store 0, this will store 1, this will store 1. Now you withdraw the clock. That means you make the clock as 0, inactive. Then they will continue to store 0011 for theoretically infinite time. But practically, over a period of time, the storage might get lost because of the discharge current or the leakage current. Okay. We are not into that right now, that you will study when you will study the digital circuits. What I'm saying over here is the logical aspect of it. Whenever the clock pulse gets active, whatever you apply at these terminals, they are said to be the parallel inputs. Whatever you apply at them, 1101, so one will get stored, one will get stored, zero will get stored, and one will get stored. Now if you withdraw the clock pulse, it will continue to store whatever you had supplied when the clock pulse was active. Now when the clock pulse will get active back again, the new data will get stored, and that data will remain stored for all times to come till the clock pulse remains inactive, right? So this is how we can store an n bit information. The design is again very modular, ith bit, and you have to repeat it as many times as the number of bits that you want to store. Suppose I want to make it a 6 bit, so I'll employ two such d flip flops also, and their inputs will be i5 and i6, right? And the same clock pulse will be given to both of them again. So this is again a synchronous design, and this is the simplest form of a 4-bit register, which can easily be extended to an n-bit register, right? So now let us see what is the problem with this simplest design. The problem is, suppose I don't want to change the data, right? And the clock pulse gets active. So there should be a way to block the changing of data even when the clock pulse gets active, right? So that we will see in the next design. This is a 4-bit register with a parallel load, right? I am employing SR flip-flops here. Employing SR flip-flops, right? Now let us look at these terminals. Clear. When this clear terminal is active, all of them will become 000. This is asynchronous clear, not dependent on the clock. Whenever this clear comes, which is is an active low, I can see these bubbles. So this is an active low signal. Whenever clear is 0, all of them will get 0 regardless of whether the clock pulse is there or not. In order for this to function as a register with parallel load, I should have clear as high or inactive. When it is high, now it will operate normally again, right? These are the clock pulses, and again you can see a bubble here means it is a negative edge triggered 4-bit register with parallel load, because it is inverting the clock pulse and providing the clock input to all of them, but it is synchronous nevertheless, synchronized at the negative edge of the clock pulse. So these two signals are explained this way. Now let us see that this load terminal is 0, right? The clock pulse is active, clear is inactive, but load is 0, right? Consider a condition when clear is inactive, clock pulse is active, that means it is low, and the load is low as well. So no loading should take place. What will happen? This is being fed to all these AND gates. So a 0 here will leave a 0 here, a 0 here will leave a 0. In fact, all of them will be 0, 0, 0 as far as load is 0, right? So a 0 at S and a 0 at R also will continue to store what all is there previously. If a 0 was there, it will continue to hold 0. If a 1 is there, it will continue to hold 1. A 1 here, it will continue to hold 1. A 0 here, for example, then it will continue to hold that 0 for all times to come, as far as this load terminal remains 0 or inactive. Now consider the case when this is inactive, clear is inactive, which means it is high, clock pulse is active, which means it is low, and load is active, which means it is high, right? So they are all enabled now because load is high. Now what will happen? I1 will come here and I1 bar will come here. So if I1 is 1, a 1 will appear here and a 0 will appear here, so it will get set. Set means q will become 1, and that is what we had supplied it with, the parallel input I1 being 1, so it stores 1. Now suppose I2 is 0, what will happen? This is active because load is high, so a 0 will appear here, and this is inverted, a 1 will appear here. So 0 1 means set is 0 and reset is 1, that means it will get reset to 0, so a 0 gets stored. So I supplied 0, 0 got stored. If I supply 1, 1 will get stored. If I supply 0, 0 will get stored. So this is how this 4-bit register with parallel load, in order to contrast with the previous design over here, when the clock pulse gets active, it necessarily changes or modifies the contents of these d type flip flops. Whatever is there, that will go here. But in this case, even if the clock pulse is active, but if I pull the load terminal to 0, then whatever is applied here, that will not be able to affect the stored data in these RS flip flops. They will continue to store the previous data only. They will be affected only when load goes high, right? So this is a better register because it can have a parallel load, or it may not have, it may have no loading at all, no loading when this load is 0, right? So that is where we will stop for today, and then we will continue from here on the next